Okay, everybody. So what we're going to be looking at today is the solutions to these midterm 3 practice problems. Now, I will say this, that your actual exam is going to be easier than this exam, and some of the longer to do problems are probably not going to appear on it. But I wanted this to be relatively complete, so I put some things on here, even though I'm pretty sure we're not going to have anything comparable in difficulty on the real exam. This probably will be in 2 parts. I'm going to write part 1 on here just because the previous 2 exams also took 2 parts to solve all the problems, and this is pretty long. So, with that said, let's go ahead and get started here. So, in notability here, I've got some blank space down here, so we will go problem 1. Kind of want lined paper. Can I do that? Let me see. There we go. Yeah. All right. So problem 1 here, we are going to be finding an absolute extrema of some function. So the function is f of xy equals, what is it? 3x squared plus 2xy, I think, plus y squared on D domain where D is a triangle with vertices -2, 1. This is not a description of D, actually. Triangle enclosed by this. 1, -1, and 1, 2. So before we get started, let's just draw what D looks like. So it looks like x values go between -2 and 1, and y values go. All right, so let's just put the points on here, actually. So we have -2, 1, so let's put that there. We have 1, -1, so let's put that here. Okay, and we have 1, 2, so let's put that there. So yeah, it looks fine. Okay, so this triangle is going to be our domain. The inside of this triangle is going to be our domain. I don't know why so little. All right, whatever. So that triangle is our domain. Now, as part of this process, we're going to have to actually look for extrema along the boundary here. So I've got these 3 sides to this triangle that I can call C1, C2, C3. And I think what I want to do, actually, I want to change the template again here. Interesting. Can't make a smaller grid. Okay, well, I guess we're stuck with it. Fine with me. Okay, fine. I don't care. Um, so there we go. That's our triangle. Each piece of that boundary is going to need to be parameterized. There's different ways to do that. One way to do that would be like this. So like C1 could be, for example, um, it goes between those 2 points that you see there. And one way to parameterize it would be to say R of t equals, and you can just do essentially the first point, like as a vector here, -2, 1, times a parameter t, and then plus a 1 minus t times the other point, which would be, I guess, 1 comma 2. Or if you want to write it in terms of x and y, right, then that would be like x equals -2t plus 1 minus t times 1, which would be just -2 plus 1 minus t, which would be 1 minus 3t, I guess. right? And then the idea there would be that if you put in a 0 in here, you're going to get 1 for the x value, which is that one. And then if you put in uh, a 1 in for t, you're going to get 1 minus 3, which is negative 2, which is that x value. So basically what this is that piece of the boundary going from this to here. Now, of course, we have to do that for y as well. We will see this. And how do we do that? Okay, sorry. 1 times t would be t, and then plus 1 minus t times 2, which would be 2 minus 2t. And then that would be 2 minus t overall, like that. So when you put in a 0 in here, right, you're going to get 2, which is that y value. And if you put in a 1 for t, you're going to get 1, which is that y value. So this parameterization for C1 works. You can do the same thing for the others. I guess I will. So for C2, for example, that's a very easy parameterization because it's just a straight line. So since it's just a vertical line like that, you can just say that the x value there is simply 1. And the y value could be t. And the t goes from, well, it goes from negative, if the y value is the y value goes from -1 to +1, sorry, +2. So -1 to +2, we could use that for our t values, which sort of illustrates I won't say a problem, but let me make that bigger there. It illustrates a problem in that here I listed the x value and the y value, and here I listed the x, the y, and a t value. I didn't list the t values for the first curve, but I set them a bunch, right? 0 to 1 would be what we have there. So last piece of the curve would be C3. This one goes that way, not that we care. And then C3 is the last piece. So what we would do is we could do like similar to what we did up here. I can say that it would be like 1 -1 times t plus 1 minus t. The other point is -2, 1, like so. And then that would be an x value of t plus -2 times 1 minus t would be -2 plus 2t. So overall, we have x is 3t minus 2. Let's just check that. If you put in a 0, you get -2, which is that one. And if you put in a 1, you get 3 minus 2, which is 1, which is that x value. So perfect. Similarly, for y, we have -t plus 1 minus t times 1. So we just have -t plus 1, -t plus 1 minus t. So it's -2t plus 1, or 1 minus 2t. Yep. So then we've got that x value there, we got that y value there, and this one would be another one that goes 0 to 1. So I wanted to parameterize that boundary before we got started. Now that we have the boundary parameterized, we can actually start the calculus here. So what we're going to do to find extrema, right? Is that what we're doing? We're finding absolute extrema on a closed domain. So what we have to do is this. So we know extrema are either inside of D at critical points, or they are along the boundary. which is why I went through all the trouble of parameterizing that curve. If you don't have an enclosed domain like we do here, then you don't have to go through this trouble of parameterizing a bunch of stuff. But this one does, so we do. So we know that we need critical points inside D or along the boundary. Let's do critical points first. So let's look for critical points first. Okay, so in order to do that, we're going to need an fx and an fy. So I'm going to go up here. No, where I have them written down. So I can do them real quick. Let me do this in another color here. So where can I write? How about right here? So we need the partial with respect to x, the partial with respect to y. So fx is going to be the derivative here with respect to x is going to be 6x. The derivative here with respect to x is going to be 2y. And then there's no x derivative there. So fy is going to be no y's. Here we have the derivative here is going to be 2x. And the derivative here with respect to y is going to be 2y. So those are our partial derivatives. So let me move them down here. So we find the partial derivatives, right? Partials. Then we are going to look for critical points by setting them equal to 0. So we have 0 equals 6x plus 2y, and we have 0 equals 2x plus 2y. Let me just double check that. Is that correct? So 6x, when we take the derivative with respect to x, plus 2y, okay. So we do have 2y there. And then partial with respect to y, nothing, 2x, 2y. Okay, cool. So no constants, huh? Okay. So anyway, if you're going to solve these simultaneously, you can do that in various ways. One way is just go to Wolfram Alpha. I mean, this is ridiculously easy to solve here. I'm going to solve it by hand, but I just want just to point out that you can do this on these problems to save you some effort. You can say just solve and then 0 equals 6x plus 2y. 0 equals 2x plus 2y, and it's going to tell you that 0, 0 is the solution, right? Very simple. But if you did want to solve it by hand, then you can solve this with any appropriate method. So like what I would do is I would say, well, I just noticed that there's a 2y and a 2y, so how about I just subtract these two equations and I get 0 equals 6x minus 2x, it's going to be 4x, and the y's cancel. So then you get x equals 0. And then once you have x equals 0, you plug that back into either equation. And you'd have like 0 equals like 6x plus 2y, but we just said that x is 0. So you put in the 0, and then you get 0 equals 2y, and then so y is 0 as well. So super easy to solve by hand, but also very easy to get a computer to solve that as well. So we've got our critical point. So let me just note that what we found here, there's one critical point, 0, 0 only. Okay, now I'm going to keep this until the end of the problem, basically, but just remember we found a critical point. Okay, now the next thing to do is we have to look for extrema along the boundary. So now look for extrema along the boundary, which is C1, C2, C3, right? That's why I did that at the beginning. So how would we do that? So we look at our function. So our original function was f of xy equals, forgot it already, 3x squared plus 2y, 2xy, 3x squared plus 2xy plus y squared. Was that it? Yeah. So we look for our extreme along the boundary. Um, so you have to do this on each piece of the boundary. So let's start with C1. It's not the easiest piece to start with, but we will. So we have C1. What is C1? Well, I parameterized it up here. So the part that I need is going to be this part right here. Let's duplicate that. Here's C1. Okay. Now what you do is you take those values, you plug them into F. So essentially what you're evaluating is F, and instead of the X, you're going to put in 1 minus 3t, and instead of the Y, you're going to put in 2 minus t. Okay, your X and your Y. So when you do that, you have 1 minus 3t squared plus 2, and then X, 1 minus 3t, Y, which is 2 minus t, and then plus y squared, which is 2 minus t squared. Now, this is definitely a case of where, you can use a computer. I mean, obviously, you are all capable of multiplying that out, but here's how I would do it. This is how you avoid mistakes on problems like these. So type in your function. So let's say f of x comma y equals 3x squared plus 2xy plus y squared, right? And I'm not even going to type this out, right? Like I could type this out and have the computer simplify it, but I'm not even going to do that. I'm going to say, there's my f of xy, and I'm going to say at x equals 1 minus 3t, y minus y equals 2 minus t. So I'm not even going to type in the long thing. I'm just going to tell it what I want, and it will just spit out the answer for me. And so, of course, the right side here, so we have 34t squared minus 36t plus 11. That's all just got t's in it. So this is my function now. Then what I need to do is I need to find critical points of this, right? This is like a separate optimization problem like you would do in Calculus 1. So I've got this, and then I know my t values are less than t in between 0 and 1. So we got to find any maximums or minimums in this piece of the curve here. So what you do is the whole optimization process from Calculus 1. So you're going to take a derivative of this new f of t. So we get 68t minus 36, right? You're going to look for critical points. So you set that equal to 0, 68t minus 36. 36 equals 68t. So t is 36 over 68. That's our critical point. Okay. Now, you can punch that into a calculator. You can even save more time by taking this result and then, asking for critical points. But I'm not going to. I'm just going to leave it here. Um, what you hear is a pocket calculator. I'm just doing 36 over 68. Lazy. 9 over 17. I could have divided those both by 4 by hand, but I did not. So we have t equals 9 over 17. Now, at this point, you can do a couple of things. I'm going to do something that's slightly longer just because I think it's easier to understand. I take that 9 over 17, and I'm just going to say, like, well, what does that mean in terms of x and y? Um, yeah, actually, that is what I'm going to do. Let's say, what is that in terms of x and y? So I've got my x up here, 1 minus 3t, and y is 2 minus t. So the x there is 1 minus 3 times 9 over 17. And the y value there is 2 minus 9 over 17. And you can work that out. I kind of regret this, what I just did, but what I wrote. So the x value there is negative 10 over 17. And then the y value there is 2 minus 9 over 17. is 25 over 17. Okay, so here's the point. Um, Going back up here to the beginning of the problem, this is somewhere on C1. We've got a negative x value of a little bit bigger than a half. So it's like, somewhere in here, right? That's the point we found. And technically, what can happen is here at that corner, here at this corner, or at this point, which is our critical point along this piece, there could be a maximum of the function here, here, or here. Um, Now, I can evaluate the function at each of these points very easily, this point, and this point, just by just using t values. I can plug in, I can take this function, and I could easily like evaluate those at like f of 0 because of the 0 and get, I guess, 11, right? I'm looking at this function. I can easily put in a 1 here, and I would get 34 minus 36, which is negative 2. Negative 2 plus 11 is 9. And then I could put in this third point that I just found, which would be plugging in a 9 over 17, and I would get another function value there, um, whatever I get. But even though I wrote all that, I am going to just save this to the end here. I'm just going to take these x and y values and write them down. So this point that we found was negative 10 over 17, comma 25 over 17. And this point here and this critical point here are, and this point here, so basically this point, and this point, those are the 3 points that I found so far to look at. And I'm not going to do any more right now. Like I could plug this in, but I'm lazy, so I'm not. Let's move on to C2. So C2 is the easy one. This one. Oops, let me just do that. Okay, here's C2. The F started out the same, right? Um, so we need F of 1 comma t now into that function. And that's why I keep this here. Remember how I plugged in my points by typing in the parameterization? Very easy to change this now to x equals 1, y equals t, and not even have to think about it. So I get, it is t squared plus 2t plus 3. So that's what we have for the equation of the curve along um, C2 right here. Now we've got to look for critical points in this. So now that we've got f of t, a new f of t, right? Different t than before, t squared plus 2t plus 3, then we need critical points in that section. So we have to go take the derivative, 2t plus 2, set that equal to 0. So we get negative 2 equals 2t. So we're going to get t equals negative 1. So we get t equals negative 1. Now, that happens to be actually the endpoint, right? T equals negative 1 is the endpoint. So there are, along C2, along this section of the curve here, we didn't actually find any points in between, right? Um, so we've only got this point here from the endpoint, this point here from the endpoint, and the critical point just happened to be down here where this point already was. So we don't have like a point equivalent to this blue point in here. So that's all we need from C2 because we didn't actually find a point. You can, when you have this point here, you can plug that in and you would just get that the x and the y value are 1 comma negative 1, which is, again, just this corner. So I don't have to put the corner twice. Okay, now C3. So let's grab the C3 from here. There's my C3. Oops, not what I want. It's the top one we don't need. Okay, so again, we need to plug that into our F to get the equation, but 3t minus 2 comma 1 minus, nope, not, y equals 1 minus 2t should do the right thing. 3 minus 2, 3t minus 2 and 1 minus 2t. Okay, so we get our f of t for this piece of the curve to be 19t squared minus 26t plus 9. And same thing we've done twice before now. We are going to take the derivative of this. So we're going to get 38t. What happened? Oh, that's supposed to be 26, but it doesn't look like 26. 38t and then minus 26. So we set that equal to 0 to look for critical points. So we have t is 26 over 38, which is going to be, both 2 goes into both of those, so 13 over 19, I guess. Okay, now we have this point that's somewhere on the curve C3. Where is it exactly? Well, we can take that and plug it into our x and our y. So 3 times 13 over 19 minus 2. And y is going to be 1 minus 2 times 13 over 19. I'm just going to do this on a pocket calculator again. So just type it in, 3 times 13 over 19 minus 2. What? Come on. Give me as a fraction. But why won't it do it? I want it as a fraction. Okay, well, we don't need this anymore. Oh, yeah, we do, actually. Going through a lot of trouble to not have to think. 3 times 13 over 19 minus 2. 1 over 19. All right. And then we have 1 minus 2 times 13 over 19, negative 7 over 19. Okay, so we've got this point. And so we have, let's say xy is 1 over 19, negative 7 over 19. And that's got to be somewhere on C3, right? It's like right here, just past 0. Um, and we've got another point. So overall, what we have come up with is this. Back up here. Overall, what we've come up with is the maximum and minimum of f has to be at one of these points. Any of the corners or any of these extra critical points we found that are on the boundary. And also, I didn't draw it here, but that original critical point we found that was at 0, 0. So any of these points that we have highlighted here, so 1, 2, 3, 4, 5, 6 points, could be the location of the maximum or the minimum of the function on this closed domain D. All right, so there's a bunch of them to work out. Let's see if we can list them. So we're going to have to work out f of 0, 0. Let me just say what we're doing. So let's say evaluate function at all possible extrema. Or, yeah, all possible extrema. We don't know if they are extrema. So the first one that we had was 0, 0. And then we had, well, any of the corners. So any of the corners count. So we got, what do we have? Just gonna duplicate this and drag it down. Maybe. Nope. Ruined that. All right. So any of these three corners are also possible locations. And I'm not working them out now because I'm going to use a computer because I'm not dumb. Okay. So those are possible locations of minimums and maximums. And then also those extra points we found along the boundary are places to look. So like the one we just found was 1 over 19, comma, negative 7 over 19. That's one. And then also there was the one we previously found, which is up here. Okay. So those are the possible locations of the minimums and maximums. So again, the way to evaluate these in an efficient way is go back here where I had typed that formula in for f and just type them in one by one. So we have obviously like 0, 0, x equals 0, y equals 0. That's just going to be 0, but we type it in. I did type it in. 0. Next one, right, we just go negative 2, 1. Oops. 9. I think we actually knew that. Um, because remember, we did evaluate at two of the corners when we did the first, one negative 1, when we did the first C1. We did it as t's, though. We didn't put in x and y. No, don't display. This one is 11. Oh, see, that's what happens. That's why you type in y equals 2 over 19. And then finally, the last one, we have whatever we have, 10, negative 10, negative 10, 10 over 17, comma, 25 over 17. But again, nope, y equals 25 over 17, like this, 25 over 17. Okay, awesome. So you do all this work, and then what you know is that the minimum and the maximum have to be somewhere on this list, right? So min and max must be on this list. So dot dot dot, the absolute max, I'll say it, absolute max is the biggest number on the list, which looks like 11. And the absolute minimum has to also be on those lists, and that's going to be 0. Right? Because everything came up positive, it looks like. So, yeah, so everything came up positive. No negative numbers. Does that make sense? I guess it does. Um, I mean, it is what it is. Now, if I made a mistake on, with one of these critical points, like the numbers on this one or something, one of these, then, maybe these numbers here are wrong and one of these actually came up the minimum or something if I made a sign error. But the process we used was the correct process here. So I've got an absolute maximum of 11, the biggest number, and an absolute minimum of 0, the smallest number. Woo! So there we go. Now this is one of the longest problems on here. Just saying. So let's move on and do number 2 now. So this one is similar, but it's find and classify the relative extrema and saddle points of um, this curve, right? And so the thing about that is that um, you don't have a boundary, so it makes it much easier than the previous one. So what do we have? Xy, 3 minus x minus y. Right. So I think that's right. Now, to look for critical points and stuff, we're going to be taking partial derivatives, and I don't want to take partial derivatives the way that this is written. So the first thing I should do is multiply this out. So I've got 3xy minus x squared y minus x y squared, right? So that's my f of xy. Now we're going to need all the partials first and second. So let's just find them. So fx is going to be derivative here with respect to x. It's going to be 3y minus 2xy minus y squared. Then our fy is going to be 3x minus x squared um, minus 2xy. All right. We're going to need fxy. So let's find that. fxy. So that's going to be the derivative of f with respect to x, and then the derivative of that with respect to y. So we're going to get 3 minus 2x. Wait, we're taking the derivative with respect to y, so minus 2x minus 2y. All right. But then we need fxx. So that's the derivative of up here with respect to x. Going to be negative 2y. I think that's it. And then fyy, the derivative of this with respect to y, which is going to be negative 2x. Okay, so there we go. Now what do we do now? So once we have all those, we can get into the work of the problem. So we have to kind of step 1 here. I mean, I found all the derivatives, but um, the first step of actually solving the problem is to find critical points, right? Those are what we are going to be classifying as saddle points or minimums or maximums. So we need to set the fx and fy equal to 0. Or, look where they're undefined, but of course these are not going to have a place where they're undefined. So here's our partial derivatives. We are going to set them equal to 0. All right. Now, how are you going to solve that? Well, it's tedious to solve by hand, right? So I'm not going to come up here, and we're going to use a computer. And after we do that, we are going to check our work as well, also on a computer, just to make sure that we did the partials right. So we'll say solve. 0 equals 3y minus 2xy minus y squared. The other one, 0 equals 3x minus x squared. minus 2xy. Um, you can solve this by hand. I'll tell you how. What you would have to do here is you would, like you'll notice there's only one x here. So you could solve this top equation. Um, Actually, yeah, I mean, I will show you a little bit. Okay, I mean, we have the solutions over there on the left, hopefully, but here's what you would do by hand, just as kind of a hint. Like, take that top equation. You notice that there's a y on all of them, so factor out a y like that. And then that gives you a couple of solutions. One solution is when y equals 0, right? Because if that's 0, the whole thing's 0. The other one would be when 3 minus 2x minus y equals 0. So you have to solve that, um, which would just be y equals, let's say, 3 minus 2x there. Okay, so you have this or this. Those are not going to happen both at the same time. But that came from the top equation, right? So that came from, like, by number that one and that two, then one gave me this. So then you can take the y equals 0. So you can say if y equals 0, then what does that mean for the second equation, right? Then the second equation would be when I plug in, um, oh, sorry, this is not, let me back this up. This is the first equation. This is the second equation. Um, So if you plug y equals 0 into this second equation, what you would get is 0 equals 3x minus x squared minus 2 times x times 0, which would make this drop off. So you would have 0 equals 3x minus x squared. But then 0 equals factor out an x, 3 minus x, you get x equals 0 or x equals 3, right? So you have those. And each of those x values goes with this y value of y equals 0 that we started with. So two critical points are um, x equals 0 from here, y equals 0, x equals 3, y equals 0. Those are critical points. But those aren't the only critical points because that only came from this. What about this? So if you have this, y equals 3 minus 2x, you can take that and plug that into here and get a completely different equation to solve. So you could say like f of xy. I'm going to type in that 3x minus x squared minus 2xy. I have no equals at y equals 3, y equals 3 minus 2x, 3x minus x squared minus 2xy, where y equals 3 minus 2x, and it tells me what I get. So I'll say, back up here, so equivalent to this, I'll say if y equals 3 minus 2x, equation 2 becomes um, 0 equals 3x minus 1 x. It says, which would give me x equals 1, x equals 0, right? So I have two x values, and those two x values go with this equation for y. So if I have x equals 1, what would the y value be? Well, you'd have to plug x equals 1 in here, y equals 3 minus 2 times 1, which would be 3 minus 2. So 1. So we have 1, 1. in addition to these two. And then also we have x equals 0 here. So x equals 0, y equals, well, it would be 3 minus 2 times x. So 3 minus 0 would be 3. So we have 3, 3. So I've got, so far, these 4 points. Okay, so yeah, that's what I got. So if you back this up and you look at what we found by hand here, um, notice I've got 0, 0, which is on this list, the bottom one, 3, 0, which is the second from the bottom, 1, 1, which is the second from the top, and 3, 3, which, wait, what happened? Oh, I wrote 3, 3 here, but it's 0, 3, 0, 3. So you can find those critical points by hand, which I just did, but you'll notice the computer was reliable for solving those. So, do you want to? Um, I don't know. So then what you got to do is start classifying them, right? So now classify in this case, for critical points. How do we classify it? The four critical points? Well, you got to evaluate this discriminant thing they call capital D in our homework, which let's find it. But it should be like D of x, y is right, like fxx at the point, fyy at the point, minus fxy at the point squared. But we'll find it in, should be 4.7. Critical point, blah, blah, blah. Second derivative test, that's what we are doing. And here it is, right? So fxx at the point, fyy at the point, minus fxy squared at the point. And then there's a way to classify it there, right? So again, we need to do this for all of them. So we need to evaluate d at 0, 0, d at, what do we got? 3, 0, d at 1, 1, and d at 0, 3. And then we will be able to interpret them according to the second derivative test here. Um, Now, in order to do that, again, we want to do this in an efficient way. Um, so let's go up here to where our derivatives are, and let's just type in all of what d should be. D, which is a function of x and y, should be equal to, it is fxx, which is negative 2y, fyy, which is negative 2x, minus fxy squared. So parentheses, 3 minus 2x minus 2x minus 2, 3 minus 2x minus 2y quantity squared at, and then we can just type them in. I'll try just as ordered pairs first, just to see if it understands that, because if so, I would be happy. Does not. So we fall back on writing it in letters and words and whatnot. No, I don't want. What are you doing? How? Why are you not suddenly lose the ability to evaluate functions, computer? I think it's because it wants it called f. It's interpreting this as a, because I used capital D here, it's interpreting that as wanting a derivative. So this is not, maybe I'll call it G. If it doesn't understand G, we'll switch to calling it F, even though that's not F. Okay, so it does understand that. Okay, so when we put in a 0, 0, we get -9. And where's fxx, by the way? Fxx is simple. It's up here somewhere. Let me just steal this. Duplicate it. Just, what? Lost it. Duplicate. Scroll. All right, there it is. So that's fxx. So um, that's negative, and if you put in 0, 0 in here, you're going to get 0, right? So I'm just going to write fxx equals 0. Okay, now the next one is 3, 0. Also -9, apparently. But fxx is going to be, well, again, it's also 2y. So if you put in a 0, you're going to get a 0 again. Then we have 1, 1. 3. And if you put in 1, 1 into fxx, you're going to get -2, which is negative. And finally, 0, 3. And we get another -9. Okay. And fxx is, if you put in a 3 in here, it'll be -6, which is less than 0. All right, so this is what we got. So what does this tell us? Let's look at what it says. Here we go. So first of all, look at number 3. If D is less than 0, then F has a saddle point. So there D was negative, there D was negative, there D was negative. So saddle, saddle, saddle. All right. Now, then if D is positive, and the second derivative could be positive or negative. So we have, for that third point, D11 is 3, which is positive, and fxx is negative. So that is case number 2. Okay. So f has a local max at that point. All right. And that is that. So that's how you classify critical points. A lot easier than the other problem that we did. We're still starting off with very long problems on this. Um, let's keep going, see if we can get to like at least problem 5 here. Um, 3 Lagrange multipliers. Okay. Interesting. So so it was x squared plus y squared, subject to, is it x to the fourth plus y to the fourth equals something? Let me look. Equals 1. Okay. All right. So first of all, this is a very simple problem, really. Um, and you don't need Lagrange multipliers. So we'll find the answer, but then we'll actually do it the way they say. So first of all, if you graph this, It's what they sometimes call a squircle, right? If it was x squared plus y squared equals 1, it would be a circle with a radius 1. That is not what I want, right? Like it would just be a circle if that was a square and a square. When you make them higher powers, higher even powers, then it basically squares off the edges to some extent. So it's like something like that. I mean, that's not a good drawing, but you get the idea, right? So they call it like a squircle sometimes because it's like a square circle. So that's what that looks like. And we're supposed to be finding the maximum of this function. Now, you might recognize this as being this being just the distance from the origin, right? Or the distance squared from the origin. So basically, the further away you get from 0, 0, the bigger this function is going to get. So what's going to happen is that the furthest away you can get from 0, 0 here is going to be here and here and here and here, and that's going to be a max and a max and a max and a max, and the closest you can get to um, 0, 0, the smallest you can make this is going to be here and here and here and here. So that's going to be a minimum and a minimum and a minimum and a minimum. So that's where the minimums and maximums occur. You don't need um, Lagrange multipliers, but they say to use Lagrange multipliers, so we're going to use Lagrange multipliers. All right. So let's get into it. So how do you do Lagrange multipliers? So what Lagrange multipliers says is that the gradient of the function should be equal to a constant that we call lambda times the gradient of the constraint function, which will be this function. Um, okay, and then also we have to add the constraint equation to the list of stuff that we have to solve. So the way we start is we need the gradients of each of these things. So we need the gradient of f. So we need the partial of this with respect to x, which is 2x. We need the partial of this with respect to y, which is 2y. We need the gradient of g, where if you, this would be g of xy. So this is like g of xy equals a constant. It doesn't matter what constant you have over here. So the gradient of g is 4x to the 3. The gradient, and then 4y to the 3, like that. So we have our partials, and then the system we need to solve for Lagrange multipliers is going to be this thing equals a constant times this thing. So 2x equals lambda 4x cubed. Then the same thing for the y component. 2y equals lambda 4y cubed. And then the constraint equation, which is x to the fourth plus y to the fourth equals 1. So this is what you have to solve. Okay, so 3 equations with 3 variables. Your variables are the x and the y and the lambda. So you need 3 equations for that. So you solve that. You can solve that in a lot of ways. Um, so how would you, well, I'm trying to think what the easiest way to do this is. Um, yeah, so I think what you would want to do here is, so like you kind of want to solve this for x or solve this for y. but you've got a problem if you do, that you can't just like divide, you can't just divide an x off. Okay, like you can't just do this, for example, you can't just go 2x equals lambda for x cubed, knock an x off both sides and have 2 equals lambda times 4x squared, because when you divided the x off that way, you're saying that x is not 0. So you have to kind of worry about that case. So like, let me number them. 1, 2, 3, right? So for 1, you can just note that either x is 0 uh, or 2 equals lambda times 4x squared. And I'm going to start writing that with the 4 in front just as 4 lambda x squared, right? So basically what I did was I knocked off an x to get this, but you're only allowed to do that if x is not 0. So I had to include a special case for when x is 0. So if x is 0, let's think about what that would imply. So if x is 0, then you could put that directly into equation 3, and you would get that 0 to the 4th plus y to the 4th equals 1. So y to the 4th equals 1, and that would mean that y has to be plus or minus 1. That's what that would mean. Now, so we've got 0, 1, and 0, minus 1 there. Now, you can check those up and to make sure that they satisfy this equation. Of course, they will for some lambda value. I don't actually care about the lambda value, so I'm not even going to bother with equation 2. You can put in like y equals 1, for example, into this equation and have 2 times 1 equals lambda 4 times 1 cubed. So you have 2 equals 4 lambda. So lambda is a half. But who cares that lambda is a half? We don't need to know the lambda value for anything. So I don't even care about this work that I just did. So that's why I'm just taking these two values. And then the other choice was that this one, 2 equals 4 lambda x squared. Now in that case, that would mean that 2 equals 4 lambda x squared. That was my other case. Or, and if I solved this for like x squared, I would get x squared is 2 over 4 lambda. And I'm just going to leave that here. Okay. Now do the same thing for the y's. So from the second equation, either y is going to be 0, or we're able to divide off a y. So either 2 is 4 lambda y squared, or the y is 0. And so if y equals 0, then you can go to that equation 3 again, which would tell you that x to the 4th plus 0 to the 4th equals 1. So x to the 4th is 1. So x is 1 or minus 1. So we get 0, 1. Nope, those are backwards. X is 1. 1, 0, or negative 1, 0. So those points, we have the other highlighted point, and then the other case was this case here, where 2 was equal to 4 lambda y squared, which would mean that lambda squared is 2 over 4 lambda, just like what we had up here. Now you can cancel a 2, right, and make this 1 over 2 lambda. Also here, 1 over 2 lambda. So what we've got here for this, x squared is that, y squared is that. That's what happens when you don't have one of those zeros going on. So you can take those, um, the x squared is 1 over 2 lambda, and the y squared is also 1 over 2 lambda, and you can plug that into that third equation, which was x to the fourth, right? X to the fourth plus y to the fourth equals 1. But x to the fourth, right? X to the fourth is x squared squared. So you can go 1 over 2 lambda squared plus, well, y to the fourth is also 1 over 2 lambda squared equals 1. And then you can solve that for lambda, um, which I'm going to be too lazy to do. I'm just going to solve it on the computer here. That's not that hard to solve, right? I mean, you can square those and add the fractions and so on, and you can get there. I'm just being real lazy here. 2, 1 over 2, I'm going to call it L. Squared equals 1. Uh, Fraught with danger. I'm going to call it, I'm going to call it X for right now. It's not X, right? It's lambda. And there's two of them. That's why, like, this is the same as this. So that's why I just did 2 times it one time. Square root 2, you end up with lambda is square root 2 or negative square root 2. Now you're like, okay, so what? But what's that mean for the x and for the y? So if lambda is square root 2, okay, then what's that mean? Well, then you have to go up and plug it into the equation for x and for y. So you have x squared is 1 over 2 lambda, and also y squared is 1 over 2 lambda. And then if you square root that, you have x is plus or minus the square root of 1 over 2 square root 2. And y is also going to be plus or minus um, the square root of 1 over 2 square root 2. All right? Now, if lambda is negative, square root 2, then when you try to do the same thing, you get x squared is 1 over 2 times lambda, but that has no solution, right? Because this is a negative number, and a square cannot be a negative. So that has no solution. So, and same thing for y. So we just have these two, or not two, but we have these x and y values. So what do we get? What we get is every combination of those. So like you have x equals like the plus square root 1 over 2 um, square root 2 plus 1 over 2 square root 2. I said x, but how about xy? So there's a point. Right? Because you have plus 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 minus minus plus minus minus. And these points here, which there are now 4 of, those are those corners. So what you've got are, we found 8 points. We found these corners, and we found these up, right, left, and down points. So technically what you would do now is you need to evaluate the function at each of the points. So like I'm going to call these, I'm going to be lazy, P1, P2, P1, P0, P1, P2, P3. You need F at P0, F at P1, F at P2, F at P3. I'm just too lazy to write them in that many times. So when you do that, yeah, the F, remember, was x squared plus y squared, right? Remember that, x squared plus y squared. So you were putting these in for x squared and y squared. You can do it by hand. Um, so it would be square root 1 over 2 root 2, comma, nope, squared, plus square root 1 over 2 root squared squared, which is 1 over 2 root 2 plus 1 over 2 root 2, which should just be 1 over square root 2, I think. And what's going to happen is it doesn't matter. These little pluses and minuses are not going to matter, right? Because when you put them in, it doesn't matter if there's a minus right here. When you square it, it's going to go away. So I think these are all the same value. Okay, and just I'm going to punch that into a calculator. Wait a second here. Hold on a second here. What is going on? This can't be right. Because I said these were going to be maximums, and I think that's clear that they are maximums because they're further away from the origin. But this is like 0.7. Um, and when we put in the one and the zeros, those are going to be ones. So something happened here. I made some kind of mistake. Oh no. Um, all right. Where did we find lambda? I found lambda on the computer. Oh, shoot. The x, this didn't end up in the denominator because I didn't put parentheses around it. I'm going to fix this right now. It'll be okay. So actually, remember this x is not the, this should have been 1 over, and that should have been 1 over. So then when you did 1 over, then this would have been 1 over. That would have put the square root of 2 on the top, right? This is 1 over 2, 1 over square root 2 is square root 2 over 2, which is square root 2. So this should have been the square root of square root 2, because this is square root 2. And this should have been, which is the fourth root of 2. So this should have been also 2 to the 1/4. So these values here, pluses and minuses, um, they should have all been just 2 to the 1/4, 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 2 to the 1/4. So then when you put these in here, 2 to the 1/4, 2 to the 1/4, you should just get, when you square these, you end up with square root 2 plus square root 2, which is 2 square root 2. So that's bigger, quite a bit bigger, right? Uh, oops. Okay. Anyway, sorry about that. So those are all 2 square root 2. And then also we had to do, there were 4 other points, ones where one of the components was 0, but again, we're plugging them in something like this. So they're all going to be 1s. Um, so then what you end up with finally at the end of the day was that all of these are your tied for the highest point. So these are all local maxes. Or, I mean, I guess they're global maxes. And these are your minimums. Yikes. Okay, so sorry about the mistake. Um, just wasn't, I just didn't type it into the computer right, and I didn't notice that I typed it in wrong. Okay, so you didn't actually need Lagrange multipliers, but we did Lagrange multipliers. Um, oh, finally we get to just do an integral. About time. Um, so we might have to stop after this one. All right, double integral x squared plus y. dA it says, and then we have a region, and our region is, oh, all right, x, 0, and 1. There was a y equals some number and then a y equals something else, but I don't remember because I don't have a memory. All right, what do we got? Y equals 0, okay, and x squared plus 2. All right, so in order to do this, you just need to make sure you understand the region. So if we look at our region for our domain, you've got y is between 0 and x squared plus 2. This is a parabola up at 2. Good enough. Y equals 0 is obviously down here, like that. And then x equals 0, x equals 1. Those are vertical lines. Um, so the region that we're looking at must be this region in between them. That's the domain. Okay. So if we're trying to set up a double integral over that region, you just go from the bottom curve up to the top curve for your y integral. So we'll go 0 to x squared plus 2 for y. And then your x integral will be 0 and 1 for your minimum and maximum x values. And then we have our function, x squared plus y, dA. We're going to do the dy integral first and then the dx integral. Okay, so you need to interpret these, draw the picture, and then you can interpret all this information as x is between 0 and 1, and y is in between 0 and x squared plus 2, right? Using these to get this, and these to get this. So you get your integral, and then from here, this should be a very straightforward integral. Just, don't, just be a little bit careful, and it'll work out. So we're doing our y integral first. So antiderivative of x squared is x squared y. Antiderivative of y is 1/2 y squared. That goes from 0 to x squared plus 2. So you fill those in. So you have x squared plus 2 plus 1/2 x squared plus 2 squared minus, plug in a 0, 0 plus 0, as often happens, and this is what we get. So that integrand I should work out. It's not going to be super complicated. It's a parabola. Again, I'm lazy. I'm going to do this on a computer. X squared plus 2 plus, I'm going to say 0.5 because I'm too lazy to even type in a half. So 0.5 x squared plus 2, and then that is quantity squared. So just double check that you typed it in correctly. Looks okay. I get, I called it a parabola earlier, but it was a squared, so it's a fourth. So what do we have? 1.5 x to the fourth plus 4x squared plus 2. Sure. We need to integrate that with respect to x. So we're going to have 1.5 x to the fifth over 5 plus 4/3 x to the 3 plus 2x between 0 and 1. Put in a 1. We get 1.5 over 5 plus 4/3 plus 2 minus, plug in a 0, 0 plus 0 plus 0. So we end up with just 1.5 over 5 plus 4 over 3 plus 2, which is 109 over 30. Now, can we check that on a computer? Let's try. So double integrals on Wolfram Alpha aren't that easy to type. Usually I do them this way. There are calculators where you can fill in everything, but I'm just doing it this way. Integrate x squared plus y from, you go 0 to x squared. Actually, it is a lot better when you're doing these if you add the fact that we're doing a dy integral. So, right, so I type it in, double check that it did the integral that you wanted. And then, you get your 3x to the fourth plus 4x squared plus 2, which we did end up with right there. And then what I'll do is I say, okay, so we did that first integral. We got to here. So I just hit that. And then I come up here and then I go integrate, wrap that up in a dx. and I go from 0 to 1, and I get 109 over 30. So I can be pretty sure that I did that right, since they seem to agree with me as well. So I only the point of doing that is the only thing I typed in, the only function I typed in was the original x squared plus y. They did all of the calculations. So, alrighty, 109 over 30. What's next? I think we can do one more and then we must stop. Reverse the order of integration. Oh no. 0 to 4 square root x to 2. So that 0 to 4 square root x to 2. Yeah. Square root x is on the bottom. Um, Sine y cubed dy dx. Okay, so hopefully I wrote that correctly. It's number 5. Hopefully I did that correctly. If I did, then in order to reverse the order of integration, which is what it asks you to do, we need to know what the region looks like. So you look at this and you see the y between these. So you say that is y between root x and 2, and then your x will be the other integral. Whoa, almost had a power out right there. X between 0 and 4. Oh, powered out again. Oh well. Shouldn't affect me. I'm recording on a laptop. Okay, so this is what we have. So you say, what does this look like? Well, you graph these on the xy plane. You have y equals 2. I don't know why I put that. It looks like y equals 3, but let's call that y equals 2. You've got y square y equals square root x. What's that look like? That goes like that, right? Um, okay. And they say x goes from 0. Okay, that is here, up to 4. And just notice that if you put in x equals 4 here, the square root of x will be, or sorry, the square root of 4 will be 2. So actually, this intersection right here is at 4. So we're looking at this section right here. Okay, so you got to know what that region looks like, okay? Um, Once you know what that region looks like and we want to reverse the order of integration, here's what we would do. So the point is that our first integral was previously this, right? The bottom curve was right here, y equals root x, and our top curve, which is behind there now, was y equals 2, right? So we were doing an integral from the bottom curve to the top curve. If you want to reverse the order of integration, then what we need to do is have the same picture, but with everything labeled the opposite way. So like I'll do that, and I'll do that, and this point is still there. Um, the point is that you've got to do your integral for x first. So this is your first integral is represented by that line segment that I just drew. So if we do that, then x is between, well, this line is x equals 0. So that can stay 0. But then what's this curve, right? We know that it is y equals square root x. But if you want it solved for x, you'd square both sides and it would be x equals y squared. So we actually need it this way, not this way. So cross that out. We need it like this. So we go from x equals 0 up to x equals y squared, like that. And then for y bounds, we just need minimum and maximum y value. And of course, the minimum y value on here is down here. This is y equals 0. And of course, this is y equals 2. So we have 0 and 2. So these bounds are the new bounds. But you can't really get those unless you draw the picture just how I drew the picture. Um, so we'll do our integral. It is still sine y cubed, and this time we're doing a dx dy integral, and our bounds are what we have here. 0, y squared, 0, 2. All right, so that's how you come up with the new bounds, and then now we need to integrate it, it says. So how do we do that? Well, idea is that it must be easier this way. So we do the antiderivative here with respect to x, and notice that there are no x's, so this is a constant. So constant dx, the antiderivative is constant times x, so we end up with sine y cubed x from 0 to y squared dy. So you plug your limits in here. Sine y cubed y squared minus sine y cubed 0 dy. Of course, this one drops off because of the 0. So you end up with antiderivative from 0 to 2 of simply sine y cubed times y squared dy. And that, that integral is possible. So you just do a u sub here. U equals y cubed. Du is 3y squared dy. So du over 3 is y squared dy. So we end up changing our integral to sine u and then du over 3. And then our limits of integration, I'm just going to plug the limits of integration here into this. So if you plug in y equals 0 in here, you're going to get 0. And if you plug y equals 2 in here for y, you're going to get 2 to the 3, which is 8. So in terms of limits for y, there's 0 and 2, but for u, there's 0 and 8. So we need this integral. So of course, the antiderivative of sine u is going to be negative cosine. So we have negative cosine u over 3 from 0 to 8. So we have negative cosine 8 over 3. Minus a minus will be plus cosine 0 over 3. So what do we end up with? We end up with 1/3 minus cosine 8 over 3 for our answer. Now, looking back over this, the reason you were asked to do this, of course, is because if you look at the original integral, you can't possibly integrate sine y squared, or sorry, sine y cubed, right? You can't do that because you can't do a u sub because there's no extra y's outside or anything like that. So you did have to reverse the order of integration here to get anywhere. So they weren't just asking you to do this for no reason. Okay, so this video is already an hour and 35 minutes. What I will say is that looking at these problems here, a lot of the problems later on are not going to be as long because we just don't have those. We just don't have the optimization problems are super long. Um, okay, so that's going to have to be it for part one. I'll have the regular test up Tuesday night, assuming you're looking at this during the summer 22 um, semester. All right, that's it for now.